In this video, we are going to be talking about the formal or precise definition of a limit. So this is the rigorous mathematical definition of a limit. I'm not sure when I'm making this, while I'm making this video, I'm not sure when I'm going to be able to teach this to you, or even if I'm going to teach it. We can go about life pretty well without the rigorous definition of a limit. We've hopefully been already doing limits in class by the time I give you this definition of a limit. This is it's very, very conceptual. All right, let's jump right in, and I'm going to tell you what the formal or the precise definition of a limit is. So the limit as x approaches a of f of x is equal to L if and only if the following is true. So this is true if and only if this is true. For all arbitrary positive values of epsilon, this is the Greek letter epsilon, so for all values of epsilon, there exists a positive value of delta, such that if the absolute value of x minus a, that interval, is between 0 and delta, so it has to be positive and less than delta, then the absolute value of f of x minus L, that difference, is less than epsilon. I remember the first time a college professor gave me this definition of a limit, and we had to do a lot with it. It was how we started calculus, and I thought I was in way over my head. I thought I was in way over my head. I thought that this was pretty wild stuff. Anyway, oh well. That is the formal definition of a limit. Now, this is not what my professor wrote on the board, though. What my professor wrote on the board was this here. This is what he wrote on the board. So, these symbols that I had never seen before, and this is what he told me the definition of a limit was. So let's go through these symbols. It's worthwhile. These are, if you are in this course, you are hopefully going to do more math. Otherwise, I don't know why you're in this course. But if you go on in math, you need to be familiar with some of these symbols that are used frequently. They are just traditional, commonly used symbols in advanced mathematics. And by the way, this definition is also called the epsilon delta definition of a limit. Okay. All right. This symbol means if and only if. So instead of writing out the phrase if and only if, you can just use this symbol. It is like a long equal sign with arrows on it. Okay? If you only go one way with it, so if you get rid of the one side of the arrow, okay, then that means implies, or then, or so. So rather than writing out these words, you could just use that symbol. This symbol means for all, for each, or for every. So this symbol, I usually extend the bar. That's how I was taught it, but this is what my math type font gave me. But I usually see it with the bar extended. So for all, for each, for every. This is the existence symbol. There exists, there is, there are, there must be. And again, I usually see it with the bar going through the other side. This symbol means such that. And once again, I usually see it with the bar going through it. So I was taught it with the bar going through. That's how I have always seen it. So you are welcome to use those. If you use this, I will know exactly what you mean. You mean such that. If you're meaning such that, that's what this means. If you use this, you're saying such that. If you use this, you're saying for all, for each, for every. If you use this, you're saying there exists, there is, there are, or there must be. All right. Using these symbols, we can say that the limit as x approaches a of f is equal to L means, if and only if, for every epsilon greater than 0, there exists a delta greater than 0, such that if the absolute value of x minus a is less than delta, then the absolute value of f minus L is less than epsilon. Okay, so that is the formal definition of a limit. Now here's a picture of it. Here's a picture of it. Here's f. Here's a. So we want to know, what is this limit? This is the limit. The limit would be right there, right? So the delta is, it gives us an interval surrounding a. Delta gives us the interval surrounding a. All right. L, or the epsilon, gives us the interval surrounding L. You can't see it, but this is a little epsilon here. Okay. So I copied this from the internet. But anyway, so epsilon gives us the interval surrounding L, delta gives us the interval surrounding A. And imagine these intervals being very, very, very short. Okay? They're very short. And so that would be, L would be the limit. All right. Let's look at a couple of examples how we might be asked that, or how I was asked that. You're never going to be asked this on the AP exam, or on my exams, unless maybe possibly a bonus. All right. Use the definition of a limit to prove that as x approaches -3, this function is approaching -30. Now we know that if we just put -3 in for x, -3 times 7 is -21, minus 9 is -30. We know that this is a true statement. But to use the definition to prove it is another story. So let's think of the definition. The definition says that for every epsilon greater than 0, there exists a delta greater than 0, such that if the absolute value of x minus a -3 is less than delta, then the absolute value of f of x, which is 7x minus 9, minus L, which is a -30, is less than epsilon. Okay, so I replaced f of x with what f of x is, L with what L is. I replaced, I didn't replace x, x stays in x, but I replaced a with a -3. Okay, so we must define a delta. We must define a delta so that what I just wrote up there is true. That's our goal. If we can define a delta that makes this true, then we have proven this limit. Okay? So we we want for this to imply this. So what I'm going to do is I'm going to focus on this side, and hopefully I can define my delta. So I'm going to focus on this side. Let's clean this thing up. We have 7x minus 9 plus 30. I can remove those parentheses easily. And then I have the absolute value of 7x plus 21 is less than epsilon. Okay. I'm going to factor out a 7. If I factor out a 7, I get 7 times x plus 3. And then I have the absolute value of a product. And the absolute value of a product is the product of their absolute values. So this becomes that. But the absolute value of 7 is just 7. And I can divide both sides by that 7. So I have the absolute value of x plus 3 is less than epsilon over 7. Well, this is great because that's exactly what I have over here. That's exactly what I was looking for, right? So we want for this to imply this. We want to know what delta makes this imply this. Well, that would be true if delta is epsilon over 7. So, for any given epsilon, we define delta as that epsilon that we're given divided by 7, and then this will be true. Okay, and so that will make the limit as x approaches -3 of 7x minus 9 equal to -30. So once we get this, we have essentially proven it. Okay, number 2. Let's do another one. Let's use the definition of a limit to prove that this limit is equal to 3. So I know if I just plug in 6 for x, we'll have 39 minus 24. 39 minus 24 is 15, and 15 over 5 is 3. So I know that this is true. So here's when x is 3. I'm sorry, I went to the wrong thing. I want to know where x is 6. So here's where x is 6, right? And I know that that will be that. So I'm finding this will be my delta interval here. And let me get a different color. This will be my epsilon interval over here. Okay, I should have done that up here on this other graph as well. Let me do that up here. So around x is -3, there's my delta interval. There's my delta. And around my -30 here, there's my epsilon. So in fact, I should have made my delta interval much shorter because delta is epsilon over 7. So this interval will be a 1/7 of that interval, the way I define my delta. Okay. All right. So for every epsilon greater than 0, there exists a delta greater than 0, such that if the absolute value of x minus a is less than delta, then the absolute value of f of x minus L, oops, I meant to write a 3 there, not an L, is less than epsilon. Okay. So we want for this to imply this. So I'm going to focus on this over here. I'm going to try to get what's inside the absolute values to be an x minus 6. I want what's inside the absolute values to be an x minus 6. So I'm going to focus on this. So I'm going to pull that over here. Alright, so I have 39 minus 4x over 5 all minus 3. And I want that to be less than epsilon. Alright, I'm going to get a common denominator of 5. If I get a common denominator of 5, I'll have a 39 minus 4x from the first fraction, and I'll have a 15 from the from the 3, right? Okay. 39 minus 15. 39 minus 15 is 24, yeah? So I'm going to write this as negative 4x plus 24 all over 5. Okay? And now from the numerator, I'm going to factor out a negative 4. I'm going to factor out a negative 4. When I factor out a negative 4, I'll have an x minus 6 right there. I'm getting closer. Now I can see that x minus 6 that I wanted. I wanted that x minus 6, right? I can see it there. I need to get rid of these other things. So now I have a product and a quotient. So this is the absolute value of negative 4 over 5 times the absolute value of x minus 6 is less than epsilon. The absolute value of negative 4/5 is a positive 4/5, right? That's a positive 4/5 times the absolute value of x minus 6 is less than epsilon. I'm going to multiply both sides by 4/5. And if I do that, I will get the absolute value of x minus 6 is less than epsilon times 5/4, right? If I multiply both sides by 5/4. And so I have the absolute value of x minus 6 is less than 5 epsilon over 4. That's what I was looking for, because there's my x minus 6. So all I have to do is define delta as 5 epsilon over 4, 5/4 of epsilon. And if I do that, then I have satisfied this, QED. So once you define your delta, you're done. Alright, so in this case, my delta was a little bit larger than epsilon. In the first one, my delta was a 1/7 of epsilon. But in this one, it's a little bit larger. Doesn't matter. Okay? It doesn't matter at all. We have proven it. Alright. Clearly, using the definition of a limit to prove a limit is rather tedious. And these two examples were for linear functions. As the functions get more complicated, the proofs get much more involved as well. Alright, that is the epsilon delta definition of a limit.